Okay, welcome back, Earth Science 11. This is video number 2. And today we're going to be, for this video, we're looking at understanding density and how it relates to temperature and atmospheric pressure. And we're also going to understand air pressure and how it helps determine the weather. Hopefully you've already seen video number 1 and answered the questions on your sheet from sections A and B. This video will help answer the questions for C and D. And also, once you're done both of these, then you can answer the summary page. That's page 3 of the document, just 4 quick examples of how one variable in the weather changes another. So, what is density? Well, density is a measure of how much of a substance you have in a given space. And the formula that we use is that density is equal to the amount of mass divided by the volume that you have. So the more stuff you have in a given amount of space, the higher the density is going to be. So we can see in these two examples here, this one is going to be the one with low density, and this will be the cube with high density. Now the volume is the same for both of these. The size of the blue square is the same for both, but this one here has less stuff, or less matter, than the one on the right with the higher density. So if there's less stuff for a given volume, that means you're going to have a lower density. Now, another way of looking at density, besides the amount of stuff if the volume is fixed, what if we fix the amount of stuff that we have, but we change the volume? So I'll give 2 examples here. So I've got a cube in both of these cases here, which has a volume in it. Now, the one here on the right has 5 objects listed, 5 objects moving around inside this box here. Now, what if I have the same 5 objects, but it's in a much longer and larger box? So in this case here, I'm still going to have the same 5 objects, so I've got the same amount of mass. However, this same amount of mass is in a very, very large area, and so this is also going to be another example of low density. And this, of course, would be high density. They're all packed in quite closely together here, and here they're all spread out. So both of these examples are examples of low density. Now, how does this relate to temperature? So what happens to the density of a gas when heat is added? So this video I have on the right-hand side, I'll play this in just a moment. This is showing a certain amount of gas molecules. Now, we're not going to change the amount of gas molecules in the video, but we're just going to heat them up. And watch what happens when we heat them up. These gas molecules start moving faster and faster and faster. They're bumping into each other, and they naturally just want to spread themselves out. So if you're, think of like being in a mosh pit kind of thing, if it's really hot, you're all pushing against each other, you're going to be moving, or you're trying to really move apart in a sense. And that's the same thing that these gas molecules are going to do. So when we add the heat, the particles want to spread themselves out or become less dense because we have the same number but in a larger volume. And then now we're going to cool it down. And once we cool it down, the particles are moving less quickly and they're going to condense and move closer together, and so they'll become more dense. Well, so that answers the question about relating temperature to density, but what about atmospheric pressure? So what happens to the atmospheric pressure when we increase or decrease the density? So let's imagine that this is our desk right here. So this is our desk at school, and this is all of the air that's above that desk. And we can kind of think of the atmospheric pressure as all the weight from the particles that are sitting on top of the desk. So at this point here, we have quite a few particles, 4, 7, 8, I don't know, I'm guessing around 20 of these particles over top of our desk because it's cold, it's dense, and they're all sitting on top. But let's play this one more time, and now we're going to heat it up so it gets to the maximum size, and then we're going to try and see how that changes our density. Well, if you look now, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've only got 12 particles sitting on top of the desk, so there's going to be less weight pushing down on the desk for a given amount of area, and so that's going to tell us that our pressure is also decreased. So the pressure is how much weight or how much force of all the particles, the force of gravity from all the particles above it is. And obviously if there's less particles, there'll be less weight. And less weight means less pressure pushing down on the desk. So on a hotter day, those molecules would be much further spread apart, so there wouldn't be as many of them sitting directly above you, and you'd have a lower air pressure. Okay, so what is air pressure really? Well, air pressure is just, like I said in the previous slide there, it's the measure of the weight of the air above you spread out over the area. So if you look at this area here, if we think of this as like a big 3D column here, well, look how much air is going to be sitting on top of this person down here. There's all these air molecules that are sitting on top of them, and so they're going to feel a lot more weight pushing down them. If you're standing at the top of the mountain, well then you've only got this little column of air sitting on top of you. So a lot less air for a given volume. So again, this is going to tell us that the higher you are, so you can say as height increases, pressure decreases. Now when we measure pressure, it's measured using something called a barometer. So this is an example of a barometer, an analog one, and it just tells you how much pressure is in there. Now the typical unit for measuring pressure is something called a millibar. So bar coming from barometer, coming from barometric pressure, which is another name for air pressure, and 1,000 millibars roughly is equal to the average pressure in the atmosphere. Now the average pressure of the atmosphere is around, it's a little bit under 14 pounds per square inch, or if we're using metric, it's around a kilogram per square centimeter. It's very close to this. So if you think about the size of a centimeter, it's not that big. And if you think about a square centimeter, it's just 1 centimeter by 1 centimeter square. On average, there is around a kilogram of air pressure pushing down on every single square centimeter of you. So if you measured yourself from the top, for example, think about how many square centimeters you would be, and think about the fact that on each of those square centimeters, there's about a kilogram of pressure pushing down on you. That means for a typical school desk, if you've got a classroom where every student gets an individual desk, you're roughly looking at around 5,000 kilograms of pressure pushing down on your desk. And that is about the same weight as a school bus. So how is it possible that you've got a school bus worth of pressure pushing down on your desk and somehow your desk doesn't break? That seems strange, right? Well, the reason for that is because air pressure acts in all directions. These little particles here, some of them are moving up, some of them are moving left, some of them are moving down, some of them are moving right. But they're all applying pressure. In each of these different directions, they're all applying pressure. So even though you have a huge amount of pressure pushing down on your desk, well, thankfully you've got air pressure underneath your desk, which is pushing back up. And so it's pushing up on the below it, and it's pushing down on top of it, and these air pressures sort of cancel themselves out. So that's why your desk doesn't collapse. Yes, there is about 5,000 kilograms worth of force pushing down on your desk, but there's also around 5,000 kilograms of force pushing up on the bottom of your desk as well. So that's what prevents it from just collapsing under the weight. Okay, well, how does air pressure relate to weather? We usually associate air pressure with clear skies. So high air pressure means clear skies, low air pressure means cloudy weather, generally speaking. Now let's take a look at the video that I've got on the right hand side here. Now what I've got is two areas with different air pressures, as I've mentioned here. So the one on the left is a high pressure area, the one on the right is a low pressure area. Well, when this video plays, it's going to remove this green line that's separating them. And if you take a look at the on the bottom, once I've removed it, take a look at this blue arrow to the right. This is telling us in general which way air is flowing. So we have a lot of air that was moving from the high pressure to the low pressure. Now you can see some air pressure pushing back to the left and some to the right. And so these have more or less reached what's called a state of equilibrium. The pressure is mostly balanced. It may fluctuate a little bit left and right, but more or less it's completely balanced. And so that's what's going to happen. Whenever we have two different areas of pressure, air is going to want to move from the area of high pressure towards the low pressure. And so if you're in a low, you're going to have air moving towards you. If you're in a high pressure area, you're going to have air moving away. And so what happens to the air that's moving towards a low pressure area? Well, the air can't go down because there's the ground in the way. And so all this new air is moving in. There's only really one way or one place for it to go, and that's going to be upwards. So as the air moves upwards, it's going to spread out throughout the atmosphere like so. And the same thing is going to happen for the or the opposite thing is going to happen for the high pressure area. You have all this air leaving the high pressure area. Well, if all the air is leaving, it has to be replaced somehow. We can't just have a vacuum forming where everyone suffocates from lack of oxygen. So the air has to come from somewhere, and the only place that it can come from is from the upper atmosphere. So what you may notice is that in a high pressure area at the ground, air is moving away, but at the top it's going to be moving towards, and it's going to be moving downwards. For a low, you have air moving towards it on the surface, and then you have air moving away from it in the upper atmosphere. Now, last week we learned about how clouds form and how precipitation forms, and I gave you the analogy of the sponge. So remember that a warm air equals something like an open sponge. So it's not being squeezed. And then cold air was like a squished sponge. Okay, so as the air in a low pressure area is being forced to rise, we know that air is going to cool, and as it cools, it is like squishing that sponge, and so that's going to force precipitation to occur. It's going to force the water to condense and form clouds. So when you have low pressure area, you're going to end up with air moving upwards. When you have air moving upwards, you are going to form clouds because it cools. Cooling means it condenses, and condenses means it forms clouds and rain. With a high pressure area, the air is moving downwards. That means that the air is actually going to be heating up, and we know that as it heats up, it means that it could hold even more water vapor. So let's say at the top, it was holding 4 out of 4 possible amounts of air. So let's say it could hold 6. It could hold 6 water molecules in a certain area, and it's only holding 4. So we got clear skies, but as it goes down, well, now it could, because it's warmer, hold even more. So now instead of being 4 to 6, now it's going to be the same 4. The water hasn't precipitated or fallen out of the sky in any way, but now you're able to hold more water. So this means that your relative humidity is going to decrease. You're going from 66% up here down to 50% down here. And the opposite is going to be true here. So maybe you are at 4 out of 6 for the number of water molecules that we can store, and as it goes up, well, now we can only hold 3 as our maximum, and we've got 4, so that means that there's going to have to be some precipitation that falls out. So this could be around 66%, and now this is 100% relative humidity, and so that means that rain is going to form. So that's why we're going to have low pressure systems leading to cloudy weather, high pressure systems leading to sunny, clear skies. Okay, and last but not least, just the summary. So you have your information sheet, your question sheet. All the information you need to answer those questions has been in these slides. On page 3 is the summary page. It lists the relationships between, or lists some of the relationships between these 4 variables. So please make sure you get that done as well, just to summarize what you've learned from this. And I hope it's been a valuable lesson. And please email me if you have any questions. Thank you.